Gennady Shvets, who is visiting us virtually from the United States, Cornell University. So the group of Professor Shvets is working on the variety of topics in modern photonics. But today, Gennady will tell us about particular direction of his research related to topological photonics. So in case if you have any questions, please either raise your hand. You may also ask the question by voice, but please make sure not to interrupt the speaker in the middle of the sentence. You can also type some questions in the chat, then I will read them. So Gennady, please, you are welcome. And it's a big pleasure for us that you have attended and given a talk on such important and hot topic. Please.
Okay, great. Thank you, Maxim, for inviting me. And it's my pleasure to give this talk. And I was told that there are lots of students, or at least some students are going to be in the audience. So I will try to make this, at least somewhat pedagogical. But fortunately, high-order topological photonics is a very new area. So in some sense, as we're moving in this direction and as we're conducting active research, we're also learning things, and in some sense, some of the recent works actually taught us some of the basics, and that makes it a little bit easier to give pedagogically minded talks. Okay, so if you're joining this talk, you probably have heard about topological phenomena in condensed matter physics and photonics. So this picture probably will not be very surprising to you.
So, Gennady, sorry, we're just seeing some slide in the middle of the presentation. So could you please?
Oh, I see it. Maybe I'm sharing something. Okay, hold on. So let me, hold on.
Yeah, now from robustness.
Sharing. Okay, so I stopped sharing. So now I'm going to start sharing again. Okay, share. And oops. So do you see the first slide?
Yes, this is the title slide, yeah.
Okay, so now I'm going to maximize. Is it maximized now?
Yeah, working. Yeah, perfect.
Okay, good. Yes. So, all right. So since you're probably familiar with topology, you may have seen this picture many times. So topology is basically a science that relies or explores robustness. And what does it mean? It means that it concerns itself with some global invariants that tell us what can be done with a system or with a structure, and structure can be broadly understood. Actually, give me a second. I'm going to switch to a laser pointer. Okay, so a structure could be some sort of a ball or a spoon or a donut, and it basically tells us what can be done with such a structure in order to transform it into some other structure without changing this invariant. And at the same time, it imposes some limits on what can be done with a system, because sometimes it is impossible to move from one structure to another without changing these topological invariants, and that would mean that basically changing from one system to another is impossible under continuous deformation. So just to give you one example of such an invariant, it's the so-called Genos invariant, which is basically the number of holes that a structure has. So, for example, if you have a donut which has a single hole, it is possible, if you imagine that you have some kind of a play doh and you start playing with it, you can deform a donut into a cup with a single handle without making any new holes. So basically using continuous deformation of this play doh. But on the other hand, if you want to turn it into a spoon, you would not be able to do that simply because that would mean that the number of holes has to change from 1 to 0, and that's not possible to do under continuous deformations. So this is how usually we think about topology, how mathematicians discuss topology in real space. But it turns out that when we move towards photonics or condensed matter systems, the whole concept of topology becomes a little bit different. So, for example, just to give you a very simple example, let's imagine that we've designed some sort of a bulk material. So it could be some photonic material, it could be some electronic material, and we've been extremely clever. We figured out how to design this piece of bulk so that electromagnetic waves just propagate around the system without any reflections, right? So now we take this bulk, right, that we've designed to suppress these reflections, and we deform it into something else. So from a box into a triangle. So obviously in real space, nothing changed to the object. We didn't have to drill any holes in it, but almost obviously, if you change from one shape to another, you will not be able to have this interesting property of propagating without reflections. You will actually have reflections. And so your outcome will be different. And that goes not only for these sorts of guided edge states that propagate around the bulk, but also it goes for example, localized so-called corner states. So again, if you have some very clever design and you have a localized state in one corner, if you change the shape of the bulk, there's absolutely no guarantee that this corner state will stay. So corner states could jump over to some other corners, so they can completely disappear. So you really have no idea what is going to happen. So what does it mean? It means that not every bulk can be deformed in such a way, and there's some underlying structure of the bulk itself that needs to be topologically invariant if we want these properties to be preserved. And in order to understand, so this is the point of what I said. So not every bulk is going to work. Okay, and if you want to understand what bulk is going to work and what bulk is not going to work, you actually have to look not into the real space, but you need to look into the reciprocal space. So in the case of electronic materials, that would be momentum space. In the case of photonics, that would be wave number space, but basically it's a reciprocal space to the real space. All right, so this will be basically the subject of my talk. I will tell you what kinds of manipulations can be done in the reciprocal space in order to create topological materials, and what sorts of phenomena we can observe. So I will start with something very simple, very pedagogical. I will introduce some notation and some of the language that people use when they talk about topology. And as always, it's always easier to work in a one-dimensional space as opposed to a multi-dimensional space. So I will start in 1D, and I will talk about very simple one-dimensional photonic and more empirical, kind of a tight binding one-dimensional models that can be used to introduce certain concepts, such as, for example, filling anomalies. And it turns out that the approaches to calculating these filling anomalies can be directly transferable to higher dimensions. So as soon as you understand how things work in 1D, going to, for example, 2 dimensions is actually not so difficult. It's almost acting by analogy. And I will introduce a very simple photonic platform that has been used in photonics for quite some time. It turns out there are still some interesting puzzles about it, and I will talk about them, some interesting discoveries. So the platform is called a calculated distorted honeycomb lattice, and I will actually discuss two platforms that we have used using this particular photonic platform, two material platforms. So one material platform is graphene. So I will talk a little bit about properties of electromagnetic waves supported by graphene. Graphene is a very interesting two-dimensional material. It's interesting for two reasons, actually. So one reason is that graphene enables confining electromagnetic waves to a nanoscale size. So typically when we think about electromagnetic waves, for example, let's say mid-infrared electromagnetic waves, their wavelengths is extremely long. In free space, for example, a 30 terahertz electromagnetic wave has a wavelength of 10 microns, so that's gigantic. So of course, electronic scales are much, much smaller. So if you're interested in bridging this gap between electronic spatial scales and photonic spatial scales, it's actually not so simple to do that. And it turns out that graphene enables you to take these photonic frequencies and shrink them to spatial sizes, which are tens or hundreds of nanometers. So that actually starts bringing us a little bit closer to the electronic scale. And so I said there are two reasons. The second reason is that graphene can actually be gated. So what this means is that its topological and in general optical properties can be changed by simply changing voltage, which is imposed between some sort of a gate and graphene itself, because when you change this voltage, you are basically injecting free carriers, electrons, or holes, depending on what the voltage is, into graphene, and it's these carriers that determine photonic properties of this material. So, for example, if you're dealing with some sort of a solid, some sort of a three-dimensional material, could be some polaritonic material, its properties are essentially fixed by nature, because nature basically fixes the size of the lattice, and all electronic, all optical transitions are fixed by that. So there's very little that we can do, but with graphene, it's actually quite different, because all optical properties are determined purely by free carriers, and free carriers can be easily manipulated. They can be ejected, they can be removed. So I will talk about topological properties of graphene plasmons. And then, so Maxime mentioned to me that there is a lot of microwave and RF work going on at your at ITMO. So I thought that it may be interesting to talk about our very recent work, which basically tries to inject a new degree of freedom. And this is a kind of a degree of freedom that I have always kind of found fascinating, especially trying to emulate this degree of freedom, because you know, when I was an undergraduate student, this concept of an electron having a spin kind of looks like it was just dropped from the sky, where the hell it's coming from. But in photonics, it turns out that you can actually emulate this degree of freedom and make it a little bit less mysterious. And this is an interesting and somewhat unexplored topic of how spin degrees of freedom can be injected into higher order topological insulators, and what happens when you do that. And it turns out that there are more topological phases that are that come about when you do this, and I will talk about that. And there are also some relatively simple photonic platforms that can be used to emulate these structures, which are still a little bit difficult to create in condensed manner, right? Okay, so now I'm jumping into the bulk of the talk. So this is the introduction. Okay, so as I mentioned earlier, if you want to understand topological photonics or topological electronic systems, you actually need to go to reciprocal phase space. And those of you who have already taken quantum mechanics probably know that if you have a periodic structure of any kind, this periodic structure supports so-called block waves. So these block waves, which are functions of the so-called block wave number and of space, of course, contain several products and several terms, and some of these terms are very well known to you, and others may be a little bit less familiar. So the first term is the periodic function. So this function is periodic within this unit cell. Okay, so when you go from one end of the unit cell to the other one, you know, this function goes back to itself, and this is true for any wave number, block number k. Okay, so this is sort of the consequence of the block theorem. Okay, so the second one is this block phase. So it basically, this is something that gives these states their propagating nature. Okay, so if k is not equal to 0, then it means that there is some phase shift when your, for example, electron is hopping from one unit cell to the next, and this is what makes it propagate. So altogether, these two terms are probably very well familiar to you. Okay, but it turns out that sometimes it's useful to introduce another phase, and this phase is a little bit less familiar. This is the so-called Berry phase. Berry is a famous mathematician in England, and how does this Berry phase come about? So one way of introducing Berry's phase is, and by the way, this phase is completely arbitrary, because when you're Schrodinger's equation or Maxwell's equations, these are all linear equations. So that means that their solutions are given up to a factor. Okay, so up to a factor, well, you can still require some sort of a normalization. So that would basically fix the amplitude, but the phase is completely arbitrary. So for every block number, you can just introduce any phase you like. So if you are running some sort of a numerical software, for example, you are running COMSOL or something like that, you know, whatever your software, whatever phase for some reason your software gives to you, you know, you can just use it. But it turns out that you can impose an additional requirement on this phase, and this requirement basically says that as you're moving through the Brillouin zone, as I'm going to show, your function has to remain continuous, and that imposes some restrictions on this phase. So for example, you know, just to give you a very simple example, let's say we have some sort of a one-dimensional periodic structure. So it has a certain band diagram, as you can see, goes from -pi to +pi. And let's say we're concentrating on this particular second band. So as we're marching through the Brillouin zone, you know, from the edge of the zone to the center of the zone, and then to the other edge of the zone, which is actually equivalent to the beginning of our trip, right? Every time we're making this step, we're basically choosing our phase, our Berry phase, in such a way that there are no jumps in the wave function. So then you can ask yourself the following question. Okay, after this whole trip is completed and you move from here to there, what is going to happen to this phase phi? Is it going to return back to where it is? Is it going to undergo some kind of a jump? And it turns out that if you have a a symmetric structure, a structure with mirror symmetry, it turns out that there are only two possibilities. There is the phase can just stay where it is, or it can change by pi. So in other words, after you've completed this journey, your function basically flips its sign. So it goes from plus some kind of function to a minus some kind of a function. Okay, so this is a very interesting example of sort of quantization of some property, of some quantity. In this case, it's a Zec phase. And it turns out that there is a simple way of kind of seeing this and understanding. So let's imagine that we have some sort of a unit cell. Okay, so this unit cell will contain two elements of some sort. We need two because we would like to basically have at least two bands. And you can think about these white areas basically any way you like. It could be two ions, and then we're adding electrons to this system. And by the way, so this distance between these ions, let's call them, is assumed to be different than the distance from this ion to the one in the next unit cell. Okay, so it could be two ions, it could be two dielectrics, for example. So ions would be confining electrons, and dielectrics would be confining optical fields. It doesn't really matter. What matters is that we can choose this unit cell and start calculating different states that exist within this unit cell. So again, could be photonic states, could be electronic states. And it turns out that there are actually not that many possibilities. So there are actually just two possibilities. So one possibility is that these states, for example, photonic states or electronic states, could be centered at the centers of these half cells. Okay, so this type of a structure is typically thought of as being topologically trivial, and this comes also from condensed matter, where we would be dealing with a trivial insulator, because basically think of these blue areas as electrons that are being confined by the ions. Or there could be another possibility where these states are actually maximized at the edges of the of this cell. So now, if we're dealing with a bulk, it doesn't really matter if the structure is trivial or topological. But as we're going to see, if there are some sort of terminations, then this could actually become important. Okay, so now let me introduce this concept of filling anomaly, because it's actually very important. So what is a filling anomaly? So what we can do, we can basically start calculating how many states we have per cell. Okay, so for example, for a trivial system, it is very obvious that we have two states per cell, and it doesn't really matter where we terminate the structure. I mean, you have a unit cell and you have two states, right? So for a topological structure, the situation could be a little bit tricky. So for example, in the bulk, we can easily calculate how many states we have per unit cell. So that's actually very easy. So you have one state here in the middle. It's not shared by any other cells. And then you have two states at the edges, and those are shared by two other cells. So it's basically 2 times 1/2 because it's a shared state gives us 2. So still we have 2 states per cell. Everything is great. And the only problem occurs is when you actually reach the end of the structure and you reach the termination, in which case you can start doing your counting, and you will quickly conclude that the last cell is actually supporting only 1.5 states. And that's easy to see. Here's one state, here's one shared state, and then there's nothing here, right? So that means that there is some sort of an anomaly if you try to fill this structure with electrons or with photons or whatever you are interested in. Okay, so one can also make this argument by looking at conduction bands. So, for example, if we have this very interesting property of chiral symmetry, which means that this third band and second band are basically symmetric with respect to the mid-gap frequency, then the way we can interpret this deficit of states is that all states below this center frequency have a half a state deficit, and then all states above this energy or frequency also have the same half state deficit because of the chiral symmetry. So altogether, we add half a state deficit plus a half a state deficit, we end up with one state deficit, and that must be somehow made up. And it turns out that it's typically made up by creating the so-called corner state. So a corner state exists when you basically combine a topological insulator to trivial insulator and start, for example, adding electrons. So you've filled all your states, and then eventually an edge state will develop at the interface. And the same basically is true in photonics, but in photonics, it's even easier to do that. You don't need to use kind of different insulators. All you can do, you can basically just choose your unit cell in a slightly different way. So this is a very simple structure that we've been recently working on. It's a plasmonic structure. So it's comprised of a metallic strip on some kind of a substrate, for example, on glass. And on both sides of the strip, you drill holes. And you can choose your unit cell. If these holes are not equally spaced, you can choose them in this way or in that way. It doesn't really matter. But when it starts being important is when you create an interface between them, and creating an interface basically means like skipping half a beat here. And what happens is that at the interface between topological and between trivial and topological phases, you start producing optical states, which, as you can see here in this figure, are confined. So in this particular case, we use the telecom frequency for our simulations, but it could be basically anything you want, right? So this is the idea of an edge state in photonics. And now, if you want to figure out this sort of a state filling an anomaly, of course, you can sort of go through fairly complex calculations, but you can also use some very simple symmetry arguments. And again, in one dimension, it's really easy to kind of follow these arguments. So it turns out that all you need to do in order to calculate the Zach phase, which, as you remember, was either 0 or pi, right? All you need to do is to calculate, and this is for a given band, by the way. So all you need to do is to calculate the number of inversion invariant eigenstates at the x point, which would be here. Also the number of inversion invariant eigenstates at the gamma point, which would be k is equal to 0, and just take their difference. Okay, so that's very easy. So here's one example. Let's imagine that at the gamma point, we have a symmetric state. At the x point, we have an anti-symmetric state. So that means that here we would have a 0, here we would have a 1. You take the difference, you basically do it modulo 2 pi, okay? And you get a Zach phase, which is basically equal to pi in this particular case. And then you can introduce a filling anomaly, which is basically Zach phase divided by 2 pi, or you would get a very simple formula like this. So you divide pi by 2 pi, and you get 1/2 filling anomaly. Okay, so it's a very simple argument, very simple procedure, right? And if you have multiple bands, it turns out that you can simply sum up over all these bands to calculate these filling anomalies. So it turns out, as we're going to see, very similar expressions can be used for higher order photonic topological insulators. Of course, you won't have just a gamma point and an X point because your Brillouin zone will be more complicated. So the formula will be a little bit more complicated, but it's basically all about counting symmetric and asymmetric structures. Okay, so the whole field of high order topological insulators and in general topological insulators is huge, and there's no way I can cover all of this. So I'm gonna stick to 2 dimensions. I'm not gonna talk about 3-dimensional topological insulators. They're not so easy to make in the lab. And I already told you basically what I knew about the SSH. So that basically leaves us with 2-dimensional second-order topological insulators that support, as it turns out, corner states that are equivalents of the H states and in the SSH model or in a 1-dimensional photonic model that I was talking about, and also churn insulators. And typically people learn about churn insulators first and then about second-order topological insulators later. It actually happens to be that way because of the way our knowledge progressed. So people kind of discovered churn insulators first and then second-order topological insulators later. But oddly enough, now that we know quite a bit about both, it turns out that from a pedagogical standpoint, it's actually easier to understand second-order topological insulators and then switch over to churn insulators, which is kind of the path that I'm going to take. Okay, so now there's a little bit of a subtlety that exists between corner states, corner charge anomalies, and so on. So let me just clarify this a little bit. Okay, so this is the argument that I made earlier. So if you have half a state deficit below the band gap and half a state deficit in bands above the band gap, and the reason it's 1/2 and 1/2 is because of the chiral symmetry. So the 2 structures are basically symmetric with respect to each other. Then you need to have some sort of a corner anomaly in order to compensate for this deficit in the bulk. And what's interesting is that this corner state may not necessarily be in the gap, or it may not be even confined. So oftentimes, we can have an anomaly, but we may not have a localized corner state. And I will talk a little bit about this. So this is actually something that has been discussed quite a bit in 2D systems, both for fiber-based photonic topological insulators and also for microwave systems. So this is from Bachel's group in Illinois. This is from Reitzman's group at Penn State. And so even though this is something that has been discussed, there are still many challenges that need to be addressed. One is, can we make these structures on a nanoscale? Another one, can we make them to be active? Can we make them to be spinful? Spinful means that in addition, there's going to be a spin degree of freedom. Can we break the Hermitian assumption and make them non-Hermitian, which is also very interesting. And, this is an active area of work in my group, but unfortunately, I won't have the time to talk about this. And there are also some subtleties about fractional invariance versus corner states, but those have been more or less solved, I think, at this point. Okay, so here's the platform that we'll be using. So the platform itself is the so-called Kekule lattice. So a Kekule lattice has a standard C6V spatial symmetry. And this is a very nice representation of what this lattice looks like. So imagine a unit cell that contains, for example, 6 atoms. And these 6 atoms, for example, 6 ions, let's say, can confine electrons. Electrons can hop from this ion to that ion within the unit cell. So, for example, from here to here, or they can hop from this ion to that ion. So that's basically hopping into a different unit cell. And these hopping amplitudes could be different in principle because, you know, in principle, the spacing between these 2 ions could be different from the spacing between these 2 ions, right? So one can basically introduce a tight binding model with unequal hopping amplitudes. And in principle, you can play around with this lattice and make it such that all distances are going to become the same, in which case you will have a degenerate case and a unit cell will no longer be comprised of all these 6 atoms. It's just going to be 1 atom in principle. So that's when T0 is equal to T1. But now let's look at what happens when these hopping amplitudes are changing, right? So we can calculate the band structure, and this was done actually by Wu and Hu quite some time ago, 6 years ago. And we can look at the symmetries of states at the, for example, below the band gap and above the band gap. And I already told you that it's really the symmetry that determines all these topological properties. So what you find is that when this hopping amplitude, so T1 is basically hopping between the cells. So when the intercell hopping amplitude goes from being smaller than intracell to being larger, okay, there's going to be a band inversion. So the symmetry of the bands, which used to be to have d-symmetry, so you're familiar with this from chemistry, there are d orbitals, there are p orbitals. So this is all quite common. So you can see that the symmetry changes. And it turns out that this changing in symmetry can actually give rise to the so-called edge states. So edge states exist at the interface between trivial and topological states. And this would be an example of a first-order Chern spin Hall insulator. Okay, so this is what this work was basically all about. So it was not about higher order topological structures. It was about first order topology. Okay.
Gennady, may I ask a question at this point?
Yes.
So I guess these topological structures should have dipole bands higher than the quadrupole bands, D-type. So it looks like.
Yes, this is a good catch. So this is a figure from this science reports paper, and I have a suspicion that maybe it has a typo, and maybe where you have P's, you actually need to have D's and vice versa, because in all our photonic work, what we find is that the trivial structures always have p orbitals below and the d orbitals above. So it's yes, it's a good catch. I never got around to checking their model, but this is but I think it's just a typo in possibly in their paper.
Yes, yes, we did this tight binding as well, checking. So they have a previous paper in PRL 2015, I guess. So, and there they write everything correctly. But scientific reports seems.
Yeah, so this was probably their error, because we don't find this to be true. Okay, so just one word about electronic versus photonic systems. So electronic systems are mostly characterized by their conductivity, and this is basically the property of the bulk. And if you have some sort of a filling anomaly, you will observe it. It's an anomaly in the bulk, and you will experimentally observe it when you conduct bulk measurements. Those could be also accompanied by some corner states, okay, by the existence of the corner states. But in condensed matter electronic systems, it's actually very difficult to measure these sorts of corner states. And in any case, oftentimes they're not localized well. They could be mixed with a bulk, so they're really difficult to analyze. In photonic systems, it's a whole different matter, because even though it is possible to measure filling anomalies, and this is actually what these two groups have done, especially the Bachel's group, what we mostly care about in photonics is the existence of localized states. In other words, energy concentration in the corners. And so this is something that needs to be additionally symmetry protected. And this is something that we do indeed observe in our numerical simulations of realistic photonic structures. Okay, so just very quickly about the platform that we've been exploring. So this is Graphene platform. So in single layer Graphene, you can, as I mentioned, you can have extremely short wavelengths, surface graphene plasmons. So this combination may look familiar to you. This is a fine structure constant, right? 1/137. So basically what this formula is telling us is that when Fermi energy is, of order some fraction of an eV, and the energy of a photon is also some fraction of an eV. For example, 1 eV is 1.5 microns, but if you go to, for example, 7.5 microns, that would be 1/5 of that. So that would be a 0.2 eV. And let's say if Fermi is of the same order, 0.2 by 0.2 is 1, you basically get an extremely sub-wavelength object, which is 70 times shorter than its vacuum wavelengths, okay? So it's very easy to see it from this formula. What's great about graphene is that you can actually control this quantity, which is Fermi energy, and it's proportional to the square root of electron density. You can actually control it using gates. And so you can inject more carriers, so you can inject fewer carriers. You can do whatever you want. And especially interesting is the concept of a metagate that we've introduced a few years ago. So a metagate is basically a gate with patterns. So in this case, it's a gate with holes. And when we apply voltage to these holes, we can actually produce some patterns of Fermi energy, which is sometimes called chemical potential. We can produce patterns of chemical potential in graphene. And in principle, this pattern can be degenerate. For example, all these holes could have exactly the same radius. So as I mentioned earlier, the unit cell would be just one kind of a hole like this. Or they could also be non-degenerate, so they could have a Kekuli distortion. So this is an example of our simulations, okay? So for example, when we want to make a trivial phase, we would basically have a larger outer hole, which is and a smaller inner hole. Okay, so this is sort of like a shrunken Kekuli lattice. And when you look at the symmetries of these modes, you get the p orbitals below the band gap. Or you can go the other way, and in fact, you can make a large hole in the center and smaller holes surrounding it, and then you have a complete flip of the symmetries of the states. So these are electrostatic potentials that I'm drawing. Something I wanted to mention, waves in graphene are basically electrostatic waves. So they can be characterized by a single number, phi, so or V potential, right? So in that sense, it's a little bit similar to Schrodinger's equation. And so then, as you can see, there is a transition from trivial to topological. And now let me just very quickly tell you how we can jump from filling anomalies or Zag phases in 1D. So this is something that I already showed you, to something very similar in a two-dimensional photonic crystal with C6V group symmetry. So instead of summing up or counting all the C2 invariant modes at the X point and at the gamma point, we just have to do exactly the same thing, but only at different high symmetry points of the Brillouin zone at the M point and at the gamma point. And it turns out that you know, for an expanded lattice, we can find that this filling anomaly, quantized filling anomaly, is 1/2. For a shrunken, it's 0. And you know, all these details can actually be read in this paper from Hugh's group. He actually put a lot of effort into classifying different lattices and so on. Okay, so now if you have, for example, a high order topological phase and you embed it into a trivial phase, you can expect a corner state. And one thing that, and this is roughly how it would look like. So you would have a domain. I mean, I drew it to be square, but in reality, it would be sort of a hexagonal structure. So you would get these corner states. But here is sort of a danger sign, because in principle, there could be some H states that are connecting the corner states. And of course, if you have H states connecting corner states will dissipate, because they will just all start talking to each other and distribute energy around the periphery. So you kind of have to be beware of these H states, which is a little bit ironic, because this is how these lattices were first introduced in order to produce H states that are covering the entire band gap. And if you want to do this, you can simply, if you have an interface between topological and trivial structures, you can nicely smooth the interface in a sense that this kind of a zigzag interface has identical radii of the holes. And you would basically have these band gap spanning H states. Okay, so the frequency here, just take a look. It's a terahertz frequency. Okay, so these are waves that have a vacuum wavelength of 70 micron. This is a long wavelengths IR, kind of bordering on terahertz. Terahertz technically is starting at 3 terahertz. But you know, if you think that 4 is terahertz, you can also call it a terahertz. But the actual spatial period of these waves is 2.5 microns, so much shorter than in vacuum, because these are polaritons, and polaritons can be extremely confined, because polaritons are hybrid states. They're hybrids between electromagnetic waves and matter waves, and that's why they can be short. But if we want to make a 2D high-order topological insulator, we don't want these H states. We would actually like to open up a band gap as wide as possible between H states. So we don't want to have a gapless structure inside the gap. And this can be done by, instead of smoothing this zigzag interface, to coarsening it. Okay, so this is a roughened interface, and indeed our numerical simulations show that we can actually have very nice localized corner states here, which are not delocalized by the presence of leaky edge states. And you can read more details in this paper. Okay. So, all right, let me just quickly, since I don't have that much time left, it looks like, let me talk a little bit about spins, not this kind of a spin, but a spin of an electron, or a synthetic spin, isospin of a photon. So, So far, everything that I was telling you, especially in the context of graphene, which supports waves described by a single function, okay, single function of potential. So those were spinless photonic topological insulators, right? Now, if you start thinking about introducing spin, then suddenly your wave functions are not just scalars. They're 2D, they're rank 2 vectors, so they're so-called spinners, okay, because your spin could be up or it could be down, right? And it turns out that these spins can be emulated with photons, and it turns out that introducing these spinful phases, especially in the presence of spin orbit interactions where different components of the spin are actually coupled to each other, one can find some very interesting new phases. And for that, if we want to do it photonically, we need to come up with some kind of a pseudospin, because photon does not have a 1/2 spin the way an electron does. And there are many ways of doing this. So, for example, you could have 2 layers of graphene, for example, on top of each other, and whether the wave is localized at the top layer or at the bottom layer, with you could say that it's a pseudospin up or pseudospin down. So that's one approach. You can also use microwave structures. For example, if you have a structure which consists of metal plate and some metallic rods inside, it supports transverse electric and transverse magnetic fields. So if you start associating a spin degree of freedom with polarization, that would also be a nice example of a pseudospin, and you can couple them too. So now, what's interesting is that when you start introducing pseudospins, you can also start thinking about different spins having different hopping amplitudes within and outside of the unit cell. And this is very interesting because in case of a real spin, electron spin, this is actually not possible, because that would require breaking time invariance. So time reversal symmetry would have to be violated. But for photonic structures, there's no need to violate any time invariance, because these are not real spins. These are completely made up. And it turns out that this opens up some new possibilities that may not even be possible to do with electrons. So here's an example of a photonic platform that we're using. So it's very simple, basically two plates, 2 metal plates, and a calculi, a distorted calculi lattice of rods with different appendages. So here you see like a hockey puck at the center of each of these rods, and another rod in the middle. So this structure has many different dimensions that you can play around with, and you have enough degrees of freedom to, for example, make transverse electric and transverse magnetic waves to be degenerate. You can couple them with different strengths, and you can introduce different types of calcular distortions. So this platform is extremely flexible. And by the way, everything is round, so you don't have to make like triangular shapes and so on, which are or some other complex shapes. So this is relatively easy to make in a machine shop. And so if you look at some of these Venn diagrams, you will see that, for example, at the gamma point, you have a 4-fold degeneracy. So why is it 4-fold? Well, it's 4-fold because you have T and TM modes. And for example, in this case, T mode has a P a dipole-like configuration, so it's a 2-fold degenerate, and TM has a default has a quadrupole geometry, so that's also twofold degeneracy. So you basically have a fourfold degeneracy here. So this is a console design, and if you change your parameters a little bit, you can actually flip the symmetry, flip the orbital symmetries of these modes. So you could have, for example, 4 D states for both polarizations at the gamma point, which is kind of very interesting. So this is just by playing with parameters of this structure. And
may I ask a question at this point?
Yes.
So do you need to perform some special optimization to ensure that the band gaps for TE and TM modes just coincide, or it comes for free in this design?
No, it doesn't. No, it doesn't come for free. So, in fact, even in our earlier structures, so those were, let me just show you. Yeah, so this is a structure from 2017. So this is, actually we published a PRL even earlier. So the structure is almost 7 years old, but in order to match the frequencies of T and TM modes, you have to play with the gap size. You have to play with the relative size of the rod, because you know, you can see this very easily, because TM modes that have electric field parallel to the rod, they're mostly controlled by the spacing between the rods and the size of the rod, and TE modes, which have electric field in this plane, they're mostly controlled by the spacing between the plates. So when you start playing with spacing between plates and the size of the rod, you can make them coincide. But it definitely doesn't come for free, because these two modes are controlled by different parts of the structure. Right.
Thank you. Mm-hmm.
So, but it's doable. It's just a matter of time. Okay, so so what we can do, for example, we can introduce a concept of a spin-polarized corner charge, and in this case, it would be basically corner charge which is related to either TE or TM mode. So you would basically have two completely independent numbers, one for TE polarization, another for TM polarization, and you know, they could be 0, could be 1/2. So in this particular case, when both modes are topologically non-trivial, you would have 1/2 for spin up, 1/2 for spin down, 1/2 plus 1/2. You would basically get a 1 or 0. So you could actually conclude that this is a topological, I'm sorry, that this is a topologically trivial structure. As it turns out, it's not, but we'll see. In this particular case, when one of the polarizations is trivial, another one is non-trivial, you would basically have one quantized size, one spin polarized charge anomaly to be 0, another one 1/2. So 0 plus 1/2, you would basically get a total corner charge to be equal to 1/2. So this is fine. So it's obviously a topologically non-trivial system. Okay, so it turns out that there are multiple phases here. So there is a phase which we call HOTI. So this is a phase that corresponds to QC is to the total charge equal to 1/2. Okay, and there is a trivial one. So the trivial one would basically have all these charges equal to 0, and the total charge is equal to 0. And then there is an interesting new phase which we call a spin-HOTI. So a spin-HOTI has fractionalized charge for each of the spins, but the total corner charge is equal to 0. So this is a very unusual structure. And so these are some of the examples that I was talking about, right? 0, 1/2, 1/2, 1/2, 1/2, 0. So this would be a spin-HOTI structure. And now it turns out that we can introduce a coupling between these two polarizations. This is the so-called spin-orbit coupling. It's done by breaking the mirror symmetry with respect to the plane, to the mid-plane. So basically this gap becomes different from that gap. So we can no longer introduce TE and TM polarizations because those are subject to this mirror symmetry. So now everything becomes mixed. And what's really interesting is that we can now introduce a new quantity, which is the projection of the spin of the state, which is a mixed state. So in this case, whether we are looking at the gamma point or at the M point, this total state is going to contain some TE polarization, some TM polarization. It doesn't really matter, but you can basically project this mixed state onto spin up state or spin down state. And interestingly enough, what we found is that for the HOTI structure, so these partial or spin polarized states are remain quantized, so 0, 1/2, 1/2, and so basically what we find is that the when we introduce this kind of a mixing, partial charges actually become unquantized. So NQ means not quantized. It's not N divided by some number Q. So so they're no longer quantized. They could be, for example, I don't know, anything basically, 1/2 minus 0.1 and 1/2 plus 0.1 or something like that. But when we add them together, we're still getting a quantized corner charge, which means that for a system like that, each corner is going to contain only one corner state. But what's even more interesting is that for the spin-HOTI phase, when we go by this definition of the spin polarized charge deficit, it turns out that it's still quantized. It's still quantized at 1/2, and that means that each corner is actually going to contain two corner states, despite the fact that we've completely mixed these spins. Okay, so we basically get two corner states, despite the fact that if we just calculated the total corner charge, we would have concluded that it's equal to 1 or 0. So we would have concluded that this system is completely topologically trivial, but it's not topologically trivial, as it turns out. So let me just very quickly run through this so we can make a very simple kind of a phase diagram. So far, what I've been talking was mostly about the case when the two polarizations are not coupled with each other. So we basically have two HOTI phases where only one of the polarizations is non-trivial, the other one is trivial, and then we have the trivial phase and two non-trivial phases. It turns out that this is true only when there's no coupling between the spins. When you introduce coupling, these two these two HOTI phases will merge into one. So the phase diagram starts looking like this. And we basically observe here three different phases. So one phase is trivial, another one is spin HOTI. So each spin polarized charge is quantized at 1/2. I mean, when I say charge, I mean charge deficit, not the charge itself. Or you can think of it as a corner charge. And then there is this HOTI phase, which has a full corner charge quantized, but separate spin polarized corner charges are not quantized. Okay, so this color scheme basically shows the spin polarized charge. Okay, so you also see this interesting dashed line. Okay, so what does this dashed line mean? It turns out that this dashed line actually corresponds to the quantum spin Hall phase. So this is a phase where you no longer have localized corner states, And the reason for that is because you develop edge states. And when you develop edge states, then obviously you cannot have corner states because they become completely delocalized. So this is a very interesting kind of a situation where, so it corresponds basically to spin degeneracy when these, so deltas are basically differences between hopping amplitudes out of the cell and inside the cell. So when they're equal to each other, we end up with a spin Hall phase. So it sort of adds an interesting dimension to how we think about dimensionality, higher order or lower order of topological states. You see in the parameter space, you see this one-dimensional line. So this is quantum spin Hall embedded inside the higher order topological state. Okay, so just really quickly, these are photonic realizations. So in a HOTI state, you have only one localized corner state. You can see it here. But in a spin HOTI state, you actually have two almost equal frequency states. And as you can see, they're distributed completely differently in space, and they have different predominances of the TE and TM modes, but they're all completely mixed in a sense that these are mixtures of TE and TM states, and they cannot be trivially diagonalized in a sense that, for example, one of them would have equal measures of T and TM, but with a plus sign, and another one, would also have equal T and TM states, but in antiphase. So you cannot diagonalize these Hamiltonians. Okay, so let me just very quickly. Yeah, I don't think this is very interesting. Let me just skip through this and show you that indeed we can have a first order topological insulator embedded in HOTI. So this would be this dashed line. And in fact, when you play with parameters and basically make sure that these differences between hopping amplitudes in and out are the same, you will indeed have these band gap spanning edge states. So this is a true spin Hall phase, and parametrically it is embedded inside the higher order topological phase, which is kind of interesting. Okay, so let me just show you how we've made this journey just really quickly. We started with a very simple SSH model. We jumped over to the second order topological insulators, a slightly counterintuitive move, but then we've concluded the strip by going back to first order topological insulators and churn insulators. And I mean, there's a lot of additional work to do, but for example, speaking of graphene, so I mentioned to you just very briefly that graphene can localize electrons and plasmons on the same time scale, on the same spatial scale. So it would be extremely interesting to find some regime where we are electrically controlling not just the optical properties, but also electronic properties of graphene. In other words, graphene particles, graphene electrons no longer behave as freely propagating particles, but in fact, they bounce back and forth between these maxima and minima of chemical potential. So in a sense, you are creating landscapes of chemical potential, not only for plasmons, but also for electrons themselves. So you're kind of creating a lattice, which is a dual use. Maybe you should delete this part about dual use, but it's dual use in a sense that it's used for confining electrons and for confining electromagnetic waves, and that would be a very interesting outcome. So, okay, sorry I went a little bit over. Thank you for sticking with me. I want to acknowledge the students who are actually doing the work, and some of them. So this is Max. So he is now on the faculty of the University of California, and yeah, others have contributed to other aspects of this work. Some of them have contributed to plasma physics aspect. Yeah, and I want to thank our funders from US Navy. And thank you for sticking with me.
Thanks a lot, Gennady. Very nice talk. So maybe I will start from the first question. Colleagues, if you have any questions, please raise your hands. So do I understand correctly that when you discuss this spin Hall phase in the two-dimensional diagram of all possible phases, that in that case, the dispersion of the H state remains ungapped. So there is no mini gap in the dispersion of the H state. And this is somehow special scenario, because in other cases you get this mini gap and then you can define all these HOTI invariants.
Yes, hold on, I'm trying to jump back to just show, okay, hold on. Yes, you're talking about this one, right?
Yeah.
Yes. So right. So these HOTI, this HOTI invariant, it can be defined pretty much everywhere. It can also be defined, you know, along this line, because you only need symmetries of the bulk modes to define these invariants. So these are properties of the bulk, but what you get here is our edge states, which become ungapped. So basically, to have, for example, corner states, you would need to gap both. I mean, it's not enough to gap the bulk. You also need to gap your edge states. So edge states will always exist, but they could be gapped or not gapped. And in this case, they're not gapped, and this is a quantum spin Hall phase.
Mm-hmm. And then I'm curious, you mentioned that it's not so trivial to diagonalize or block diagonalize the effective Hamiltonian of this system. So I wonder, is the composition of the corner states, let's say, is different from the composition of the H state in terms of how T and TM modes are hybridized?
That's an interesting question. We haven't really tried to compare the composition of the edge states and corner states, because we would have to do it for slightly different parameters. Because when we're basically, when we live along this line, we cannot identify corner states because they're no longer localized. Yeah, but I guess it's possible to just compare maybe some, you know, points in parameter space that are very close to each other. Yeah. No, I don't know. We haven't done this.
Mm-hmm. Because it seems that at least in some special cases, the Hamiltonian should be definitely block diagonalized. In some other cases, you get some off-diagonal block responsible for couplings of the pseudo spins or whatever. But then it's like should have some easy interpretation. So yeah, very interesting and of course very fresh idea. Then I also had a question regarding some previous part of the talk where you're discussing C6 symmetric lattice, and so the question is regarding its higher order topological nature. So as you mentioned, the mini gap in the dispersion of these breathing honeycomb lattice H states depends somehow on the way you terminate the lattice. On the other hand, we like know that these higher order invariants are determined only by the bulk properties. So my question is, can we say that this C6 symmetric structure is a truly higher order topological insulator?
Yes. So this is a yeah, it's a good question. I mean, I think that that we can, because we can also calculate, for example, charge anomalies, and that's something that we can do in the bulk. So. But now this kind of coarsening. So your question basically comes down to how can we be certain that this corner state is not somehow coming from the H states that are somehow interfering and producing a corner state, that maybe we have a corner state, but we don't necessarily have a charge anomaly. So this is something that we can check, and we can demonstrate that there is a charge anomaly there, and that the number of corner states is, when they exist, is equal to what is predicted by charge anomaly. So, I mean, what type of a proof would you consider sufficient?
Well, I believe your group had a nice work on Kagome lattices, where you discussed that the origin of those corner states, which stem from the H states. Could that be possible that some similar mechanism is working here?
In the C6, well, it's yeah, it's certainly possible. It was, you know, Kagome lattice was suspicious to us from the very start, because it's, you know, it has non-vanishing polarizations and the non-vanishing corner states. So we always suspected that it's probably not a real, that these corner states are not related to charge anomalies. This is, you know, this is a C6b structure, so we didn't have those concerns, but yeah, I guess it's something that's worth looking into. I'll think about it. We haven't run into any kind of paradoxes so far with this structure, but maybe we didn't look at it.
Yeah, because we were studying recently this paper on Kagome and found out a lot of new for us.
Yes.
Okay, and then maybe the last but not the least question. So you mentioned that in solid state physics, we have a nice recipe to prove that the structure is topological by measuring, let's say, sigma xy, so this whole conductivity. But in the case of photonics, we mostly are looking at the localized field distribution and then conclude that here is the topological state. So do you anticipate some measurement in photonics which may prove the topological origin from some bulk properties?
Well, I mean, in microwave systems, you are probably familiar with science paper from the Illinois group. So they have been able to measure the exact charge anomalies. So, but it's in a microwave range. For the optical range, it's a little bit harder, but we have a collaboration with Dmitry Basov at Columbia, and he actually have an ANSOM, a near-field scanning optical microscope that enables you to measure the density of optical states. So measuring these sorts of density of state anomalies can only be done using some kind of a localized instrument. So it would have to be done with an ANSOM. But it's a tough problem, because you would have to do it over a very broad range of frequencies, because you know, it's a structure that has many bands, and they span, you know, the entire terahertz range. So it may be a little bit challenging, but this is something that we've been thinking about.
Right, thank you. So maybe some other questions from the audience. So I see a question in the chat. So could we possibly construct a quantized invariant in the spin orbit coupled case, like Z2 invariant for quantum spin Hall effect, which is quantized even when spin orbit coupling is present?
Yes, I think so. I mean, so for example, this has actually been done before. So you're probably talking about, hold on.
The last part. I guess this was the question about the last part.
Yes, I know, but I just want to show you this work from Wu and Hu. Yes, so Wu and Hu, they were able to construct these invariants as Z2 invariants. So I don't think there's any problem.
Yeah. But maybe if Maxim can ask by voice. So I guess it's the question about higher order topological invariant, because Wu and Hu, they evaluated just spin Chern number or Z2 invariant, just the conventional one.
Yes, I mean that in the high order spinful case, so the spinful HOTI, if there is some spin orbit coupling, then we have the sum of the corner charges, which is like integer, but each of them is some number which is not quantized.
Yes.
So could we construct possibly some invariant in this case? So the high order topological invariant.
I mean, the only one that we were able to construct, hold on. So, oh, maybe I skipped. No, it's the next one probably. Yes, so this is so these are the only ones that we were able to construct. So this and then the sum of these two, right? So QC would be basically the sum of the spin polarized charges. So these charges are not quantized. And you can you can calculate them, but whatever they are, they always so you see non-quantized, but whatever they are, they always add to 1/2. So I don't think we have any other invariants. And by the way, this is something that may be of interest to you. So these spin projections, right? So we've projected them on spin up and spin down. So in our basis, it was like T and TM polarizations. But we've also did the same thing for X direction of spin. So you can do it for spin right and spin left, if you like. And these invariants were confirmed both for the spin HOTI phase and also, for the HOTI phase. But for the HOTI phase, of course, you have to add them up.
Mm-hmm. So the right invariant is the sum rather than the spin charges.
Yes. For this particular phase, it has to be the sum. Yeah.
But the difference is not meaningful. Like in spin Hall effect, you take the difference of the Chern numbers for the pseudo spins. So is it any sense in taking difference?
Oh, I see. Taking difference, and maybe in the case of yes, especially in the case when you have a quantum spin Hall phase. That may be a good idea. We haven't looked at that.
Yeah, that's very interesting topic for us as well. So
okay,
it's a
unfortunately I have to run. So my wife already is telling me that we have to drive to work. So yeah.
So thank you for attending us and giving really nice talk. So we'll keep in touch and hope
that would be great.
Some new ideas appear. So thanks to everyone.
Thank you
for
attending the talk, and let's try to collaborate.
Yeah, so see you. Goodbye.
Bye, everybody.